Oh, can you hear me, guys? Okay, good. So, in the previous class, we learned about the RISC-V instructions. It is because in this course, we will cover RISC-V instructions. So that means the computer hardware, I saw actually in the previous class, I mentioned that computer hardware is just a machine that receives instructions and then generate the output promised by instructions. And then I also mentioned that this output, the generated output by computer machines is the changes of data, and then data in register file and memory. Then I believe most of you know about the memory, because when we mention the computer system, we frequently mention the size of the main memory. That is the main memory of the computer system. So, and then I believe most of you already know that if a computer system have larger memory, then the performance of a computer system may be better. Yeah, maybe better, not always better. So, and then so actually in when the program runs on the computer machine or computer system, then the user data, so all kinds of data is stored in the main memory. So actually our data is stored in the storage devices such as NAND flash or SSD or hard disk drive, HDD. But when this program is executed by CPU, then this data is moved to main memory, and then the programs are executed by CPU. So, and then also we also learned about the instruction set architecture. So the instruction set architecture defines the instruction that will be executed by CPU or computer processor. Also, instruction set architecture defines some additional information, such as the number of register files or some operation mode of the computer hardware. So I said I already uploaded the RISC-V instruction set manual. So it's a little bit long, but if you are interested, then you can read the instruction set architecture manual of RISC-V. So, but as I mentioned in the previous class, the size of the instruction, actually the complexity of instruction set of RISC-V is much simpler than the commercial instruction set architecture, such as ARM or x86. So we learned about the instruction set architecture. Also, you need to distinguish the instruction set architecture and microarchitecture. So instruction set architecture just define the how instructions are defined, and then the defined instructions are executed by computer hardware. But microarchitecture is the how to design the processor hardware. So I told that even though it's normal. So even though the instruction set architecture is the same, but microarchitectures can be different. An example is the Intel Atom processor and Core series processor. And then the microarchitecture is different, but these Intel Atom or Core CPUs can execute the same binary programs, So So binary is the compiled program from the high-level language. Then when the program is compiled, then this binary program contains the certain instruction set defined by some architecture family, such as x86 or ARM ISA. Okay. Okay, so this is instruction set. So I just covers the arithmetic instructions. Okay, let's start from here. I briefly repeat these arithmetic operations. So I mentioned that the arithmetic operation actually is very simple because we are already familiar with these arithmetic operations. And if you use a calculator, then calculator also have these arithmetic operations such as add, subtract, multiply, and divide. So the computer also performs these arithmetic operations such as add or subtract. Actually, the RISC-V has the base integer ISAs. So RISC-V ISA defines this base. What happened? Then this integer ISA just includes the add and subtract, not multiply and divide. And multiply and divide is the kind of extensions of here, RISC-V ISA. So actually the basic arithmetic operation for integer ISA, so the base ISA of RISC-V includes the just add and sub instructions. Just two, that so there is no multiply and divide operations in the base integer ISAs of RISC-V. Interesting. Then the form of this arithmetic operation is very simple. So this is the operator. Operator. And then these three variables are operand. And then it's the same to our arithmetic, real world arithmetic operations such as A plus B. So in the real world arithmetic operation, this is an operator. So these are operands. Okay. Also, I also explained the meaning of this instruction, like add A, B, C. This is the add A equal B plus C. Okay. And then in this time, I will talk about the operands of the computer hardware. So this is the real world arithmetic operation, like 1 plus 2 equal 3. So I said this is the operator, these are operands. So in the real world, we just handle decimal numbers such as 1, 2, 3. So these are the decimal numbers. But in computer hardware, so computer hardware is the kind of digital systems. And then I said that digital system just handles the binary number. So this means the number. So binary number is just to have two kinds of numbers. we always know 0 and 1. So it is because this 0 and 1 can be represented as the electrical signals. Normally in the digital system, we represent 0 as the low voltage, and then 1 with the high voltage. So VDD, supply voltage, and the low voltage is equivalent to the ground. So, and then when we program with C or C++ or Python, then we just store these numbers in the variables such as A equal 1, B equal 2, and then C equal A plus B. So, so I said that in the computer hardware just handles the binary numbers, actually binary signals, and then these binary signals can be represented as the electric signals. So, and then these data or operands are stored in the memory. Okay, so like and then it is firstly stored in the main memory such as DRAM, and then when this add instruction is executed by CPU, the RISC-V instruction, so add instruction of RISC-V just can handle the data in register files. So that means this add instruction cannot access this DRAM memory directly. And then this add instruction just can access the register file. So RF means the register file. And then register file is just actually very small memory. So it's a small memory. But this small memory is much faster than DRAM. That's why this arithmetic operations just handles the data in the register file. So actually it is when we declare this instruction in the high level language, then the memory space for this variable is assigned to the DRAM, so main memory. And then how about the data? Data is represented as the binary number such as the 0, 0, 0, 0, 0, 0, 1, and then how about 2, 0, 0, 0, 0, 0, 1, 0. So, and then this binary data is stored in the DRAM. And then this data is transferred to the register file because I said the arithmetic and even arithmetic operation, arithmetic instructions of RISC-V can just handle the data in register file. So that means if the data exists in DRAM, then this data cannot be directly accessed by add instruction or sub instructions. And these are the arithmetic instructions. So, and then this data is moved to the register file and then accessed by this add instruction. So, the previous example, we just used the variable name here, but actually these variable names should be represented as the register file number. So I will explain later. It's just this is the overview of the operands. So actually add, so T0 FG. So these are the variable name of this C program, but actually this instruction should be represented as to use the register file like x1, x2, x3. So in the RISC-V ISA, this X means the register file, and then the following number means the register file number. Okay. And then I said this register file is the small memory, so register file has the number like here 1, 2, 3. So actually this number is the index of the register file, and then there is a space for data. So that means, so XO means that this is the register file space number 1, and then in this space the data will be stored. So X2 means that, so actually the meaning of this instruction is that X1 is updated by X2 plus X3. Okay, so that means it's the same way. So X2 means that it's a register number 2, so access this space indexed by number 2. So then this add instruction use the data here in the X2, register X2. Okay, X3 is the same. So that is the operand of the computer hardware. Okay, so I will explain. So the register operands. So actually there are two kinds of operands in the RISC-V instructions, register and immediate value. So I will explain about the immediate value later. So I'll first in this here. So I will explain about the register operands. So register operand means that this register operand means the data stored in the register file. Okay. So the arithmetic operand instructions use register operands such as add, x1, x2, x3. And then the number of registers are defined in ISA. So I will repeat. Number of register files, number of registers is defined in ISA. So what does that mean? So I said the register file is the very small memory space, and the register file is just a collection of registers. Okay, and then these number of registers are defined in ISA, instruction set architecture. So that means the size of the register file, and then the size of the register file is defined in ISA. So that is some architectural, so this architectural definition. So software. So in the previous class, I mentioned the architectural states, the register file and main memory. And then I said that these are the output of the instruction. So that means the output of the hardware, that is the interface between software. So the change of this data is revealed to the software. Okay, so that's why this register file size and then the number of registers is defined in instruction set architecture. That means the software needs to know the organization of this register file. Okay. And then the RISC-V has the 32 64-bit register file. What does it mean? What does that mean? What is this 64-bit? It's the size of a single register file. Okay, that is the size of single registers, single register, a single register. So what does that mean? This register can store 64-bit data. 64-bit is the 8-byte data. So byte is the 8 because the byte, 1 byte is 8-bit. Okay. I believe everyone knows this. So this 64-bit defines the size of a single register file. And what is this? 32. There are 32 registers. Okay. So that means in the this is the register file. So then this is the size of the data. This is the 64-bit. And then I said the register file has the register file is accessed by index numbers, like such as this register number 1, 2, 3. So the number actually this is the hardware and then it's a computer hardware. So number starts from 0, 0 to register number is 0 to 31 because there are 32, yeah, right, registers. So this is this register file is the small memory, and it's very fast memory. So because this memory is very small and very fast, and then this is very precious space for data. If the memory is very fast, then it can be accessed in a very short time. So that means the performance. So we learned in the chapter 1, the performance of a computer will be higher if the data exists in this very fast register file. Okay. So because this register file is very fast, and frequently used data is stored in this register file. But this register file is managed by software. So what does that mean? So let's start from this example. So in this example shows the C code. So I said that this C code is translated into the assembly, and then assembly is translated into the machine code, machine language. But the assembly and machine language is mapped to 1 by 1. So that means one line of assembly instruction can be mapped to the one line of machine language instruction. So 1 by 1 mapping. So actually when we use the high level language, then we directly use the variable names such as F, G, and then some long names such as the very long variable. So, but I said in the RISC file, these data should exist in register file if the data is computed by arithmetic instructions like add and sum. What does that mean? This data should be translated into the register number. Okay. So in this example, we just use the variable name here, but actually in the compiled assembly code, we can find the register numbers. Okay. So this is this register size is the register size is a 64-bit, but it is because this textbook. So in this course, we just handled the 64-bit ISA, like IV64I here. So you can find the different kind of instructions, such as the basic instruction, such as IV32I. So that means that is the 32-bit instruction. And then 32-bit instruction just means that the size of a single register is 32-bit, not 64-bit. So for this IV32I, a single register file size is just 32. And then this 32-bit data size is called the word. And the 64-bit data size is called the double word. Okay, such as DW and then W. Okay, and then so actually I already explained about this register file, register in the computer processor. So actually I copied this definition from Wikipedia. So you can read this Wikipedia definition, but as I said, the register is the very small and fast memory. And then this small and fast memory is accessed by some instructions in the RISC type computer processor. Okay. And then also I explain about the organization of the register file. So I said there are 32 registers in the RISC-V. So this number of registers are defined in instruction set architecture. Also, you can, so this is, and then the width of this register represent the size of a single register. So this size of the single register is determined by the 32-bit instruction or 64-bit instruction set, like IV32I, IV64I. So I already explained. Okay. Also, the computer processor can have some special purpose register, such as program counter. But we will learn about this program counter in chapter 4. So just ignore this program counter this time. So I said that this program counter is the special purpose register. So that means these 32 registers are general purpose registers. General purpose. Okay, it's called the general purpose registers. So that means any data form can be stored in these registers. Okay. So and then this slide shows some typical purpose of these 32 registers in RISC-V. So that's it. That is just a recommendation. So, but this is some typical purpose of registers. So that means, so this X means the register in RISC-V, and then I said the number means the register number, the register file. So actually this X0 is the special register in RISC-V. So X0 just stores the value 0. And then this value is not changed. So that means if we perform the add x0, x1, x2, so what is the meaning? x0 is updated by x1 plus x2. So if 1 is stored in x1 and 2 is stored in x1, the result is 2. So then the x0 is should be updated by this number. But by definition, the x0 contains the constant value 0. So what does that mean? Even though this instruction is executed, x0 does not change it. x0 is always 0. Why? So this is some special register in the RISC-V. So why does RISC-V use this x0 register? Sometimes we need some no operation. So this no operation just consumes 1 clock, but no operation does nothing in the computer processor. You sometimes need this type of operation. How about this instruction, add x0, x0, x0? So this instruction actually does nothing because x0 is not updated by new value. So sometimes we can implement this instruction. No, this instruction is called the nope because this is the no operation. And then sometimes we need this nope operation just to consume 1 clock. So this instruction can be applied, can be used for implementing this nope operation. Sometimes we can use the always 0 value, like add x2, x0, 1. So what does that mean? Just performs the x0 plus 1. So that means it's a 0. So just store 1 to the x2. So because using these always 0 value from x0 register, we can implement some specific instruction. Okay. Also, other registers have a typical purpose of each. Typical purposes, such as x1 is used for return address of a function, and then x2 stack pointer, x3 global pointer, and so we can find some several typical purpose in this RISC-V registers. So compiler engineers, make the compilers. So compiler engineers, this information is provided to the compiler engineers, and then when the compiler engineers assign this register number to the instruction, then they try to keep this as some typical purpose of registers. Okay, that is just the typical purpose. 예. 저거는 사실은 좋은 질문인데요. 사실은 add i를 써야 되긴 하는데 이거는 이제 좀 나중에 설명을 할게요. So we need to use the immediate operation to add I. Yeah, it's a convention. Just a typical purpose. So for example, if compiler does not have find enough available registers, then compilers can use any registers, like X3 or X4. Okay, so but this is normally compiler keep these rules. Okay, let's see the same code. So this is the C code, so high-level language code, and then we use the variable names GHIJ. But in the previous slide, we directly use these variable names, but I said the data should be stored in the register file, in the registers, in the register file. So in this example, we assume that these variables are assigned to the register number x19, x20, such blah blah blah. So instead of add T0 G H, add T0 G H, we need to use the add the instruction, and then T0 is the target of this instruction, and then so T0 assigned to the register number x5, so x5, and then G the 20, x20 and x21. So actually we need to use these registers. Okay, the compiler maps this variable to the registers. Okay. So I said, let's start from here. So in this architectural stage, I mentioned the register file, and then now I need to mention main memory, because this main memory is also the architectural state. Okay. And memory. So I said the program is stored in the main memory, like DRAM, the DRAM. And then this arithmetic operation just access the register file. But as I already mentioned, the number of general purpose registers in RISC-V is just 32. And then if you write some programs, then we already know that the number of variables used in our program is much larger than the 32. But yeah, right, much larger than the 32 number of variables. So that means our variables cannot be stored in the register file. So actually, when the variable is declared like a =1, then this variable space is assigned in the main memory like A, and then this data is stored in the memory space DRAM. But as we already learned, this add instruction needs to access the register file. So this add instruction cannot directly access the variable A. So what should we do? We need to transfer this data from DRAM to register file. Right, it's obvious, right? And then this time, so we need each operation. We need data transfer operation, and then this data transfer operation is also called memory operation, because the main memory is only accessed by these data transfer operations. Okay. So the RISC-V application program works like this. The data is stored in the DRAM, and then this data is moved to the one of the registers by data transfer instructions such as load instruction. Okay, load instruction. So this load instruction read the data from the DRAM and move this data to the ownable register file. Okay, and then after that, this arithmetic instruction access the register file and then performs the define operation. Okay, so actually the all of data defined in the program is stored in the main memory. So actually all type of data like array data, structures, dynamic data, so all kinds of data is stored in the DRAM, the main memory. And as I explained, the data should be transferred by this memory instructions. One is called the data transfer instructions, and so this data is transferred to the register file. And then after that, like C, so such as A equal 1, B equal 2, C equal A plus B. So when we write this program, so as I already said, these variables are assigned in the main memory. That means the C is also assigned in the main memory, right? But when this instruction is translated into the assembly instruction, the RISC-V instruction, this instruction need to use the add instruction, the arithmetic operation, right? But we already know that the target of this add instruction, arithmetic instruction, is a register or register. So it's different. The space is different. So that means the result of this add instruction is stored in the register file, and this updated value should be transferred to the DRAM, where the data variable C. So that means that actually that is the address of C, pointed by address of variable C. So this instruction is also required. So it's a data transfer from register file to main memory. And then this instruction is called the store. Then the formal instruction is called the load. So load is the memory to register file is the load instruction. And then register file to memory is the store instruction. So there are two kinds of actually data transfer instructions in RISC-V, so load and store. Okay, so it depends on the direction of the data transfer. Okay. Also, you need to remember that memory is byte addressed. So what does that mean? Byte addressed. So when you use the C program, so I frequently take an example from C because C is very tightly connected to computer hardware. So like when we use the A equal 1, then that means in the main memory, the A is assigned to a certain space of main memory, and then the data is stored in this assigned space, right? So if there is a storage, and then in order to access the data in the storage one memory, we need the address, right? Because the address just represents the location of data in the memory. So we frequently use the and sign to represent the address of variable. So that means this is the address of variable A, So this address can be represented as the number. So for the apartment, is every house has the house number. It's the same actually. So every house can be indicated by house numbers like 101, 102, house number 101, 102, such as that. It's the same to the memory. So the memory space can be represented as the address number. So it's called the address. So address number 1 covers the 1 byte space. So 1 byte is the 8-bit. So byte address means that address number 1 covers 1 byte of space. Okay. So for example, if the address number is 1, that means it's a hardware. So we need to start from 0. So it indicates the first 8-bit of space in the main memory. And then how about address number 1? So just the difference is just 1. So that means the next 8-bit data space in the main memory. That means the byte addressable. So most of the computer system use the byte address mode. So that means address number 1 represents the 1 byte. So you need this is very important. So you need to remember this. Also, the RISC-V use the reader-endian system. So what is the reader-endian? So actually, so for example, in the C code, the integer type occupies the 4 byte. Okay, and then so that means this 4 byte of data need to occupy address number, for example, 0 to 3. Right, but we need to decide how this byte data how this byte data is assigned to the address number 0 to 3. And then there can be 2 different directions, like a reader endian and a big endian. So this is the example of a 32-bit integer, like 0A, 0B, 0C, 0D. And then, so this is the hexadecimal number. So this 2 digit represents the 8-bit. 알아야 되죠? 베이직이죠, 베이직. 베이직 of the computer system. So 2 digits of the hexadecimal occupies the 8-bit data. So reader endian means that, so this is a 32-bit integer number. So reader endian means that this RISC-V, the least significant bit of the 32-bit integer is assigned to the small number of memory. For example, address 0. And then next, 1 byte of data is assigned to the next space of memory, like 1, 2, 3. So what does that mean for the reader endian? The RISC-V, the least significant bit, the least significant part of data, byte of the data, is assigned to the smallest address space. That is the reader endian system. Big endian is different. So it's a reverse opposite of the reader endian system. So that means the MSB is assigned to the smallest address number. That is the big endian. RISC-V is the reader endian system. Okay. So yeah, so it's also important. So we need to know how the data is assigned to the main memory in the computer system. So we need to understand this little endian and big endian systems. Okay. So this is some unique feature of the RISC-V. The RISC-V does not require words to be aligned in the memory. So what does that mean? so actually there are, I said there are two kinds of data transfer instructions, but these data transfer instructions have some what's that, is a different format, such as based on the size of the data. So for example, for the load instruction, there are three kinds of load instruction in the RISC-V instruction. So LB, LW, and LD. So LB means that is the load byte, and then LW is the load word. So LD means the load double word. So byte is the 1 byte, word is 4 byte. So LH, there are 4 different kinds. Sorry, let's start. So there are 4 kinds of data size: LB, LH, LW, LD. So B means byte, H means half word, load half word means the word, this is the double word. So size means there is the 1 byte, so 2 byte, and then the word means the 4 byte, and then the double word is the 8 byte. So when the load instruction is executed, when we need to set the address of data. So for example, when the load LB is executed, we just use this target register file, and then we need to calculate the address of main memory. So LB is okay because it's the size is the byte, so we can use any number for this address. But how about this word and double word? The size is the 4 and 8, so the half word is a 2. For the normal other ISA, the address when the LH or LW and LD is used, then addresses should be multiple of data size. So that means the LH is used, then the addresses should be even number, like 0, 2, 4, blah, blah, blah. We cannot use odd number for the LH because it's not the multiple of 2. But RISC-V supports this non-aligned accesses for LH and LW and LD instructions. This is also a unique feature of the RISC-V. But some other ISAs also support the multiple of data size for this data transfer instructions. Okay. So this is the example of the memory instructions. Like this is the C code. You can find the array data A and A, and then you can find the index of the array A, like 12 and 8. And then H is the scalar data. So in this example, H is stored in the X21. So let us assume that the data is already stored in the register file. Okay. Now about A. So what is the base address? Base address of array A is the address of A0. And then what is the address of A1? Then so let us assume that the size of size of array So that means the size of element of array A is the double word, that is 8 byte. So let us assume that the base address, the address of for this A0 is the 0, 0, 1, 0. So what is the address of A1? So when the array is assigned to the main memory, so there's no answer, so I will explain. So this is the main memory. So the A0 is assigned here, then normally the A1 is assigned the it's next to A0. Then what is the address of the A1? So I said that the size of one element is 8 byte. 8 byte. So then the address is the A0 플러스 A, Y. 그렇죠. 네, 맞습니다. So address is the 00001 A. Correct. 네, good answer예요. So in this example, the base address is stored in the X22, and then also we know the index of the element here, then we can calculate the address for these A12 and A8. Okay. So what does this instruction mean? This is the load. So LD means the load double word. So that means this instruction just read double word data from main memory and then move this data to register file. So this is the target of this instruction. So data is stored in the X9. So this is the base address of A. So this is the address of A0, 64. And then this means that A0 plus 64. So this 64 is the offset of this array. Actually, the offset of the address. So that means this means the A0 plus 64. So that is the A, right, address of AA. So it's just load data from AA in the main memory and store this data to X9. So currently this value of AA is the register X9, okay, by this instruction. And we perform the add X9, X21, X9. So what does that mean? It just calculate the X9 is the A8 plus H, right? Because this is the H and this is the A. Okay. Store instruction. So that is the store double word. So it read the data from the X9, then store to this address. The space in the main memory pointed by this address. So you already know that this is the address is the A0 plus 96, and then 96 is 12. What that means is the A12, right? So what does that mean? So X9 now has this value. So this value is read from the register X9, and then this value is stored in the main memory pointed by this address. And then this address we already calculated here. This address is the address of A12. Okay. So this example shows how the data transfer instructions are used in the executed in the computer processor. Okay. Then, so this slide was just summarize what I explained until now. So register is fast, memory is slow, but register size is very small, very small. But memory size is it's large. When they compare to the register file, the memory size is very large. Recently, we used 4 gigabyte. It's larger than 4 gigabyte of memory normally, right? Even the smartphone is the 6 gigabyte or 8 gigabyte of the main memory. It's very large. But the size of the register file just includes the 32 registers. Okay, it's very small. Okay, now I will explain about the immediate value. So actually previously one student asked about how can we use the number directly in the instruction. So we can use the immediate instructions. So, and then this number is called the immediate number. So unlike the register operands, the immediate number just to represent the each number, right? So 4 means just 4. So, and then when the immediate number is used, we frequently, so normally use add I after the instruction. So when you use the add, then this add need to use the register operands only. But if we use the add I, then this add I use the immediate value. So immediate number, immediate value or immediate number. So what does that mean? So target register file is x22. Then this also the one of operand is the register operand. So it's the value stored in the x22, and you can use this immediate value. So 4. So meaning of this instruction is the x22 plus 4, and then store the final result to the x22. That's it. It's simple. But you may think that why do we need immediate operands? So we can use it like this: a equal 1, b equal maybe a x22 stored in the x22, and then c equal p plus a. That's it. So we can use this instruction instead of immediate value. But why do we use the immediate operand? So when we write the program, we frequently use the very small number, right? I think it's true. Yeah, we don't have, yeah, that's right. Oh, it's a good answer. You don't have to transfer data. That's great. Great answer. And then that's right. So when we write the programs, we frequently use very small numbers such as 0, 1, 2, 3, 4. And then it is true. But if there is no immediate instruction like a equal 1, b equal a, then this instruction need to use the load instruction. So that means in the main memory, assign the space for A and then store in value 1, and then using load instruction, transfer this data to the register file, and then we perform the add instruction and store the result to the register file. But usually, this data transfer instruction takes very long time because main memory is very slow. That's one problem. Also, if there is no immediate instructions, then we need to use the load instruction to transfer data from the main memory. Then it will consume one clock also. But we already know that we frequently use very small number, 1, 2, 3. And then this small number can be included in the instructions. So we will learn later, but instructions are represented as the binary numbers, and then this instruction also has the fixed size for RISC instructions, RISC type instructions. So, but this small number can be easily included in the instruction data. So instead of use this additional load instruction and the memory space, we can simply add this small number in the instruction code. And then it will reduce number of instructions. Also, it will save the data transfer time from the memory. So good. It's good for the performance. So that this immediate instruction use this idea, make the common case best. So we know that small constants are very common. So we frequently use small constant numbers, and then immediate operands avoid the load instruction. So we can improve the performance. So we can reduce the instruction count. So performance. So performance is the inverse of the CPU time. The CPU time is the instruction count multiplied by IPC multiplied by T, clock period. We can reduce this instruction count, then we can improve the performance, right? Okay. And then this immediate number should be represented as the binary numbers. So actually, then we need to know how the numbers can be represented as the binary numbers. So I think it's a very simple. So I think I don't need to explain this binary number because actually this is the 이진수, 맞죠? So it's just the 이진수. So actually, we can easily represent our decimal. We can convert our decimal number to the binary number easily. So I will skip here. But how can we represent the minus number? So negative numbers. So this is the 2's complement signed integer, and then we just inverse the sign of the MSB in the binary number to represent the negative numbers. And then this minus sign, so the inverted MSB represent the size of 2 to n minus 1, and the number of bits of the binary number is n. So if the for example 1111, so 4-bit number, that represents the minus 1. How? That represents the minus a is the 4, 2, 1, plus 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 So -1, right? So that means the MSB bit is the leftmost bit. If the MSB bit is 1, that means negative number in the 2's complement number. So that means we can use the instructions such as add I, x22, x22 -1. So this -1 should be represented as this minus number of the 2's complement integer. Okay, it's also it's not. I think it's not. I don't think it's difficult. So I think I will skip here. So skip here. Let me explain. And then to sign the negation. So negation means that we just change the sign of the number, like +1 to -1. For the binary number, for the negation of the binary number, we just invert the every bit and then just +1. Okay. So for example, +1 is 0, 0, 0, 1. 맞죠? Then for the negation of the 0, 0, 0, 1, we just inverse the every bit, like 1, 1, 1, 0, and then +1 is the 1, 1, 1, 1. So that is the -1, that is the +1. And then -2 plus is the same, 1, 1, 1, 1. Just invert every bit, 0, 0, 0, 0, +1, 0, 0, 0, 1. This is the +1. This is the -1. Very simple. So negation of the if a certain number is the x, then -x is the negation of x +1. Okay, easy. And then sign extension. So I said that MSB of the number is the sign bit, but we sometimes use the sometimes we need to extend the sign number of bits of a certain number. For example, 11112 to 8 bit. So how can we extend this number? So if this number is the signed number, then this MS bit represents the sign of the number. So when we want to extend to this number to the 8 bit, then we need to repeat the MSB number like this. But if this number is unsigned number is just 자연수죠, natural number, unsigned number, natural number plus 0. Then we need to just add the 0. So the sign extension is different based on the type of numbers. So signed number or unsigned number. Okay. So signed extension. Just repeat the MSB, and then for the unsigned number, we just add 0 to increase the number of bits of certain binary numbers. Okay. So this is also obvious. So there are two kinds of extended load, like LB and LBU. So LB means the sign extended load. So that means, so LB is the load byte. It's a load byte. So that means read the byte data from the memory and then transfer this data to the register file. But we know that the size of the register file is 64-bit. And then this is the byte data. So data size is different. So in this case, we need to extend the we need to increase the number of bits in this data. But if we use the LB, then it means the sign extent loaded by. So that means we just repeat the MSB to the this additional bit. But if we use the LBU, it's the zero extended load by, we just add the zeros. Okay, so they can be different. Okay, so I think this sign and unsigned numbers are easy. So I quickly covers this part. So if you don't understand this part, just read the slide text. Okay, I'll stop here. Sorry for quick. Okay, do you have any questions? Okay. So then I need to explain. Sorry for delayed class. Actually, okay. So I posted the lab assignment on the Blackboard, and then actually we, as I announced it, we have lab assignment for designing RISC-V CPU using system value law. But for this lab assignment, you need to install the RTL simulator called ModernSim. So this lab 1 is just a preparation for the lab assignment. So for this lab 1, you need to install the ModernSim simulator and then write the very simple code, simple gate like AND OR gate, and then write the test bench, very simple test bench, and then simulate your code using the ModernSim. That is just for preparation of your following lab assignment. So it's okay. 네, 이게 요거는 가능합니다. 지금 질문이 올라왔는데, 예, 저거는 이제 그 인스트럭션에 그렇게 정의가 돼 있어요. 우리가 이제 어드레스를 계산할 때 아웃셋을 옆에다 써주면은 그거를 더하기 해서 이제 어드레스를 계산한다. 라고 I4에 데피니션이 돼 있어요. 그러면은 하드웨어는 그거를 구현해서 해야 되는 거고요. 이게 뭐죠? 다운로드 링크를 통해 다운로드가 되지 않습니까? 어떤 거를 말하는 거죠? 다운로드 링크가 어디 있죠? 프리 소프트웨어를 막아놨네. 되는데? 글쎄요, 저는 되는데 왜 안 될까요? 그 슬라이드랑 비디오 링크를 하는 것 같은데, 글쎄요, 저는 되는데. 링크는 제가 그 피아자에 그냥 올려놓을게요. 왜 안 되지? So I don't know the reason. 네, 글쎄요, 저는 되는데. 네. 어쨌든, I will post the link of the slides and video on the 피아자. Okay? Okay. Okay. Thank you for listening and see you in the next class. 수고 많았습니다.